Good day everyone. In the previous lecture, we have discussed about the classification of instruments. So in that we have seen that there are many different type of instruments that are possible. In today's lecture, we'll be discussing about PMMC type of instruments, that is permanent magnet moving coil instruments. We'll be discussing about its principle, operation and working. Then we'll be discussing about the moving iron type of instruments. We'll be discussing about its principle, its type, its construction and working. Then we'll be discussing about electrodynamometer type instruments. Here also we'll be discussing about principle, operation and working. And for all these three instruments, we'll be looking into its torque equation, and based on the torque equation, we'll be defining how these instruments can be used for DC and AC measurements. As we have discussed in the previous lecture, there are many different type of instruments possible. Let us start discussion about a permanent magnet moving coil instrument, PMMC. It is also called as PMMC, that is permanent magnet moving coil instrument. So as we have discussed yesterday, moving coil instruments and permanent magnet moving coil instruments, its constructions are similar. The only difference is that here in a moving coil instrument, instead of a fixed coil, what I'll do is I'll be using a permanent magnet. That is why this is called as a permanent magnet moving coil instrument. Now this type of instrument, it works on the principle of d'Arsonval movement, that is the d'Arsonval galvanometer. It works on a which principle? The same principle is utilized here in permanent magnet moving coil instrument. Now here we can see that there is electromagnetism. The effect of electromagnetism plays an important role here. Now for example, if two magnets are kept in this manner and a coil is kept in the center, and I am passing some current through this coil. When current is passing through this coil, what will happen? This will become a electromagnet, and already some permanent magnets are kept here. So both this magnetism because of the movable coil and magnetism because of the permanent magnet, both will interact, and because of this interaction there will be a movement of the coil. The coil will either rotate in this direction or it will rotate in the opposite direction. Now this is the very basic principle based on which my PMMC type of instrument is going to function. Now coming back to the construction part. Now the construction of a PMMC instrument, it has 5 major parts. That is, a PMMC instrument will have a moving coil, it will have a magnet system, it will have control, damping, pointer and scale arrangement. So these are the 5 important parts in a moving PMMC type of instrument. Now let us look at the construction. This is how a PMMC instrument is going to be constructed. Now the first thing that I said here was that it has a moving coil. Moving coil is nothing but, let me zoom the picture. This is the permanent magnets that I was talking about, and this portion is the moving coil. This portion, that is, there is a small gap in between magnet and moving coil. A air gap is there. If we look closely, we can clearly see that there is a air gap between the moving coil and the permanent magnet. So this arrangement, it is the moving coil arrangement. Now the moving coil arrangement is wound with turns of enameled or silk covered copper wire. Now for making this turn, a rectangular aluminium piece is taken. This rectangular aluminium piece, this is called as the former, and on this former some windings are made, and because of this the coils are kept in such a manner that it can move freely in the field of permanent magnet. The coil itself is responsible for producing electromagnetic damping, and the former that we have used, that is also responsible for producing eddy current damping. So this is the moving coil system. Then we have the magnet system. The magnet system is nothing but the permanent magnets that we are using, because this is the field in which my moving coil is going to rotate. Now the magnet system, because there is a development of materials like Alcomax and Alnico. These materials have high coercive force, so it is possible to use smaller magnets which has high field intensities. So earlier, that is, if I wanted bigger magnetic field, I had to use bigger magnets. Now smaller magnet, that is, reduction in size of the magnet is possible. Also this increases the magnetic field strength. Now moving further, we can see that so this helps in reducing the size of the instrument. Earlier this if I used a big magnets, because of my big magnets my size of my instrument had to be something like this. Now if I'm using smaller magnets, the size of my instrument can be reduced. Now this is a great achievement because of the development in high alloys like Alnico and Alcomax. Now we can see here that to obtain longer movement of the pointer, we use concentric magnetic arrangement. We use concentric magnetic arrangement means concentric magnetic arrangement is nothing but, so this is the concentric magnetic arrangement. So that if I am using rectangular magnetic arrangement, what will happen? The movement of my coil will be reduced. Now what I am doing is I am using concentric magnets. Because of this I can get larger span of movement in my pointer. That is, my pointer can move greater, it can move for greater angles movement is possible. The third important part that I have is control. Control is nothing but, as we have said, control can be achieved using gravity control or spring control. Now here what we have done is a spindle is there. This is the spindle. On the spindle I have attached a former, and on this former my moving coil is wound. Here I have bearings. This is called as my jewel bearings or pivot jewel bearings, and to this jewel bearings in between I have some springs. Now I am achieving spring control here. Now here we can see this is the bearing and this is the spring. This spring is for returning for making my pointer return back to its zero position. Now here I am using phosphor bronze hair springs I am using. Now these springs also help, that is, to the coil. I have to bring current to the coil. So this spring, it also helps in taking current inside and out of the coil. Now I can also use ribbon suspension I can use. For example, if a ribbon is there, to this ribbon also I can attach my coil. Now what will happen is this ribbon will twist. Now as this ribbon is twisting, what will happen? Because of the mechanical strength of this ribbon, this will try to bring the coil to its previous position. So it is also a type of suspension. So for the control, torque can also be achieved using the ribbon suspension. The fourth part is damping. Damping is nothing but, as I have earlier said, as I am using a aluminium former. Now this aluminium former helps in producing eddy currents, and because of this eddy current damping I am getting here. The fifth arrangement is pointer and scale arrangement. The pointer, as we can see that the pointer, it is carried by the spindle. The pointer is attached to the spindle because when my coil is moving, what will happen? This pointer will also move. That is, in this direction and in this direction my coil can move. Based on that, my pointer can also make movements. Now the pointer's construction has to be pointer has to be lightweight construction, light in weight. Why it should be light in weight? To reduce stresses on the bearing. So as I was saying yesterday, for counterbalancing, a counterweight is kept in the opposite arm of the pointer. Now here we can see that the the tip of the pointer is twisted. It is twisted to give a knife type arrangement. Now why this knife type arrangement is there? This knife type arrangement is there so that, for example, if this is my scales, and if my pointer is very thick, it will for example it will cover more number of dots or lines it will cover. Now if I am having a thin tip, if my tip is thin, what will happen? It will cover only one. For example, it will cover only this. So I can get accurate readings I can get. Now for removing this, what is done is, near the scales a mirror is kept. Now because of this mirror, what will happen? This is the pointer. Now if I am getting reflection here, that means there is a parallax error. If I am getting a reflection here, that is, if I can see two pointers, that means parallax error is there. So my reading is wrong. If I am looking from the top, no reflection can be seen, only the pointer is seen. So that means there is no error is there. So these are the 5 different parts of my permanent coil moving permanent magnet moving coil instrument. So the first is moving coil, next is my magnet system, next is my control, the spring that I am using, next is the damping, that is the aluminium former that I am having, next is my pointer and scale arrangement. Now to this pointer also a counterbalance is kept. So these are the five different parts of a permanent magnet moving coil instrument. Now if it was a moving coil instrument, these magnets would have been replaced. In place of these magnets I would have used coils. So if I would have used coils in place of permanent magnet, it will be moving coil instrument. Now in place of coils, if permanent magnet is used, that becomes PMMC type of instrument. Now let us look at the three-dimensional construction. So in the three-dimensional construction, it is quite clear that I am using radial type of magnet. Radial type of magnet is used. This is the moving coil. The moving coil is attached to a spindle. Spindle is attached to the pointer. Now here I am having some springs I am having. So what is happening is my pointer can move for a my pointer can move in a radial manner, it can move. So here two springs are there, the upper spring and the lower spring, both are used for control. Now let us look into the torque equation. Moving to the torque equation, the first is my deflecting torque. Deflecting torque is because of the current that I am giving. Because of the current that I am giving, the current is passing through the coil. Because of that only I am getting deflection. Now this coil, it will have n number of turns, and the magnetic field, it will be B, that is the permanent magnets that I am using. The magnetic field strength will be B. The movement will also depend on that, and it will also depend on the area of the coil and the current that is passing. So N is nothing but number of turns in the coil, B is the strength of my permanent magnet, A is the area of the coil, and I is the current that is passing through the coil. So we can clearly see that the N, that is number of turns, cannot be changed, area cannot be changed, and the magnetic strength of the magnet that I am using, it cannot be changed. So this NBA, I will be denoting it as G. So it clearly means that my deflecting torque is equal to G into I. Then I have spring control. As I am using spring control, therefore I am having TC is equal to K theta, as we have discussed in yesterday's class. So I know that if my pointer is stopping at this moment, initially this was the position of my pointer, if my pointer is stopping at this moment, it means that if current is removed, it will return back to this position. If current is removed, it will return back to this position. So it means that spring that is kept, it is trying to take it back to its initial position, but the current that is applied is trying to bring the pointer to this position. So it means that final steady state, this deflecting torque and controlling torque both are at equilibrium. So here I can write TD is equal to TC, that is at final steady state position, TD is equal to TC. I know TD is equal to G into I and TC is equal to K into theta. So I can clearly write theta is equal to G by K into I. So from this expression, it is quite clear that the current is directly proportional to theta. Theta is nothing but the angular position, how much my pointer is moving from 0, the angular position theta. So whatever deflections is made, it is directly proportional to current. So that is why I am saying my PMMC instrument can only be used for DC currents. Why it can only be used for DC currents? Because angular position is directly proportional to current. Now for example, if my current is plus, it means my pointer will move to this direction. If my current is minus, it means my pointer will move to this direction. Now if I am using DC, it means that if I am having a plus, then only my pointer will stay at this position. Now if I am using an AC, what will happen? My pointer will keep on fluctuating from first position and the second position. It will come here, then it will go back here, then come back here, come back here. In this manner, the pointer will keep on fluctuating. Therefore, the PMMC instrument, it cannot be used in AC type of instrument. The second type of instruments that we are having is a moving iron instrument. Now moving iron instrument is also somewhat similar to moving coil instrument, but here we can see that in moving coil instrument, the center portion, it was a coil. Now this coil, what I am going to do is I am going to replace it with a piece of material, of which piece of conductor. This coil is replaced by a conductor. This is the only change in my moving iron instrument. Now in moving iron instrument also, it works on the principle of electromagnetism. Electromagnetism means, for example, if I am having two coils, and to these coils if I am passing current, this will become an electromagnet. And if this is becoming an electromagnet, in between this, if I am keeping a piece of iron, or it can be any piece of material which is able to attract by a magnet. Now what will happen? This coil, as it has become an electromagnet, it will try to attract the iron piece. Now because of this, based on this principle, my moving iron instrument is working. Most of the common ammeters and voltmeters that we are using in laboratories are moving iron instruments. When I am talking about moving iron instruments, here when the coil is excited, it becomes an electromagnet, and the iron vein, the piece that I am using, we will be calling it as veins. The iron vein, it moves in such a way that is, it tries to increase the flux of the electromagnet. This is because the vein, it will try to occupy a position where the reluctance that is felt by this iron vein is minimum. Now we can see that the moving iron instruments are of basically of two types, that is attraction type and repulsion type. Now let us start discussion about what is how a attraction type of moving iron instrument will work. So as I have said earlier, I have coils. So these are my fixed coils. Now to this fixed coils, current will be passed. Now as currents are passed, this will become electromagnet. So as this is becoming electromagnet, what will happen is this will induce a magnetic field in this area. In this area, a magnetic field will be introduced. Now here we can see that the coil is flat and it has slot openings, that is some former material is kept. On this former material, the coil is wound. Now the moving iron that I am using, so this is the moving iron part. The moving iron that I am using is a flat disc or a sector which is eccentrically mounted. Eccentrically mounted means, for example, two discs I'll use, and these two discs, it will be fixed to my moving system. Now for example, if this is a spindle, to the spindle, two discs I'll just attach, or eccentrically mounted, I'll eccentrically mount two discs. Now when the current flows through the coil, when the current flows through these coils, what will happen is a magnetic field is produced, and the moving iron, the outside portion, it has weak magnetic field, and the inside portion, it has strong magnetic field. The moving iron, it will move from the weak magnetic field to the strong magnetic field. So we can see that the iron, it is getting attracted. So when the iron is getting attracted, the pointer will move. Now we can see here that the controlling torque is provided by springs. Now this is the spindle. Now for example, if I am this is the spindle, that is, this center part is the spindle. Now to this spindle, I am having two vanes connected. Here a spring is connected, here bearings are there. Now it is clearly, we can see that controlling torque is provided by springs, but also we can use gravity control. For example, if my instrument is vertically mounted instrument, or my instrument is vertical type of instrument, here I can use gravity control. As shown in this diagram, gravity control can also be used for vertically mounted instrument. Now here we can see that if I am going for eddy currents. Now eddy currents, what it will do, it will try to minimize the operating magnetic field. So I will not be going for eddy current damping. Instead of that, I will be going for air friction damping. So as we have seen yesterday, a piston is there. This piston is inside a chamber which is closed. Now this is connected to the pointer. Now here I can get air friction damping. The damping is provided by air friction with the help of a light aluminium piston which is attached to the moving system, which moves inside in a fixed moving chamber which is closed at one end. Now the next type of instrument that we are having is repulsion type of instrument. So here we can see that the force that is operating is attraction force. That is the iron vein, it is attracted to the magnetic field. So this is attraction type of instruments. Then we are having the next is repulsion type of instruments. The repulsion type of instruments, in the attraction type of instrument I used only one vein. In repulsion type of instrument I will be using two veins I will be using. That is the difference. For example, what I will do is veins, I'll use veins which are similarly magnetized when the current flows through the coil. For example, this is the arrangement. This whole arrangement, it is kept inside the fixed coil. Now when it is kept inside the fixed coil, now what will I do is I'll pass a current through these coils, and because of this I'll use two pieces. Let me sketch it again. This is my fixed coil. Inside this fixed coil, what I am doing is I am keeping two iron pieces. Now this will turn into a magnet in this manner, and this will also turn into a magnet in this similar fashion. Why? Because both the pieces they are kept inside the same field. Because of that, both these pieces will get magnetized in the similar manner. So as both are getting magnetized in a similar manner, a repulsion force will act in between these two pieces. So this is the very basic principle based on which a repulsion type moving iron instrument is designed. So here we have two designs, that is radial type instruments and coaxial vein type instrument. So this is the radial type of instrument and this is the coaxial type of instrument. So in radial type of instruments, we can see that the veins are radial strips of iron. That is, there is one vein which is fixed and one vein which is movable. Now what will happen is the fixed vein is attached to the coil and the movable one to the spindle of the instrument. Now as this is attached to the spindle, what will happen? This will keep on moving. So looking at this, this is a movable field. Here one vein is attached and this is the second vein that is attached. Now this vein, it is able to move in this direction. Now based on how the field is, what is the strength of the field? Attraction, that is weak movement or strong movement will take place. So this is my radial type of instrument. Then I have coaxial vein type instrument. Now in coaxial vein type instrument, the radius, they both are having the same axis. So this is my fixed vein and the fixed vein is little bigger, and this is my movable vein. The size of the movable vein is little smaller. The field and moving veins are sections of a coaxial cylinder. That is, sections means it is not a complete cylinder, it is just a portion of this cylinder, that is sections of cylinder. Here also we can see that the controlling torque is produced by spring. Now looking at this, we can clearly see that. Now for example, this is my movable coil, and to the movable coil a fixed vein is kept, and next to the fixed vein I can see a movable vein is kept. Now these movable vein, it can move over the area in this manner. That is, depending on the strength of the magnetic field, the movement will be weak or the movement will be strong. Now here also I can use gravity control. That is, if the instrument is vertically mounted, I can use gravity control. The damping torque, here also it is produced by air friction, as similar to the attraction type instrument. The operating magnetic field in moving iron instruments are very weak, therefore we will not be going for eddy current damping. It is not used here because introduction of permanent magnet is required for eddy current damping. This will distort the operating magnetic field, or this will weaken the operating magnetic field, therefore we will not be going for eddy current damping. The moving iron instruments are unpolarized instruments, that they are independent of the direction in which current passes. That is, these type of instruments, it can be used for both for AC and DC. Now how this is possible? We will look at the torque equation, and based on the torque equation we will see how this can be used for AC instruments and for DC instruments. That is, whatever may be the direction of current in the coil of the instrument, the iron iron vanes are always magnetized in such a manner, that is, for attraction type of instrument always attraction force will be there, and for repulsion type of instrument always repulsion force will act in a moving iron instrument. Now let us look into the torque equation. Now looking at the torque equation, we will have to work on the principle of conservation of energy. The principle of conservation of energy says that whatever electrical energy I am giving, that electrical energy, some portion will be stored in the coil, that is the moving coil that I am using. Inside this, as this is an inductor, inside this some energy will be stored, and it will also be used for the mechanical work done, that is the movement of the pointer will also be dependent on what electrical energy I am supplying. So this works on the principle of conservation of energy, that is electrical energy supplied is equal to electrical energy stored in the moving coil and the movement of the iron. Now we can see that here we know that the mechanical work done, it is the product of deflecting torque and how much the pointer is moving. For example, depending on how much angle my pointer is moving, it is dependent on that, the work done is dependent on how much angle it is moving. The next we have electrical energy supplied. We know that E is equal to d by dt of Li, differentiating that I get I dl dt plus L di by dt. Now to calculate what is the electrical energy that I have supplied, the formula of energy is power into time. Power is nothing but V into I. I have calculated what is the value of E. What I will do is, to this E I will multiply I and dt. So multiplying that I get I squared dl IL di. So this is the electrical energy that I have supplied. So I am marking it as equation 2. I have already got equation 1. Now the change in stored energy, I know that the energy stored in my inductor is equal to half Li squared. Now this is the initial energy that is stored. Now when applying current or when there is a movement, what will happen is there is a small change, that is small increase in current and small increase in the inductive portion. Therefore this is the amount of increase in energy. So what I'll do is I'll have to subtract both these quantities, and after subtracting both these quantities, what I'll do is second order and higher order terms I'll neglect, and I'll get IL di IL into I into L into di plus half I squared dl. So this is my third term. So as I was earlier saying, the principle of conservation of energy. Now to this equation, what I will do is I'll substitute all the values. I'll write equation 2 is equal to equation 3 plus equation 1. Now doing that, the final term that I'll get is Td into d theta is equal to half I squared dl squared. So this is, from this I can get my deflecting torque. Deflecting torque's value is id half into I squared dl by d theta. Now as I am using spring control, I know that my control torque is equal to Tc is equal to k into theta. At final equilibrium position, both these values are same. Therefore what I will do is I will equate Td is equal to Tc, and equating that I get theta is equal to half I squared by k dl by d theta. Now from this expression it is quite clear that theta is directly proportional to I squared. Now for example, in DC quantity, if the value is plus 5, what I will get is the deflection will be plus 25, right? Now if I am using AC quantity, if AC quantity, it will keep on changing, that is from plus to minus. When it is plus, that time also I will get the deflection to be plus 25. When it is minus 5, that time also I will get the deflection to be plus 25. That is theta is directly proportional to I squared. Whatever current I am applying, whether it is an AC current or whether it is DC, whatever may be the current, the operation of this instrument will be it will give constant operations. It will not keep on vibrating when AC supply is given. The next type of instrument that I have is electrodynamometer type instrument. Now when I am using the other instruments, that is when I am using moving iron instruments. Now when I am using moving iron instruments, here what I have to do is I will have to calibrate my instrument separately when I have to use it for AC. That is the necessity of AC calibrations of moving iron instruments and any other type of instruments. This cannot be correctly calibrated, right? Because of this, I'll have to use transfer type of instruments. Transfer instruments are nothing but using DC supply I can calibrate that instrument, and the calibration that I have done for DC will hold true if I am using it for AC. That is, there is no need of separately calibrating for AC. Because of this, an electrodynamometer type of instrument it began to be used. Now this, it works on the principle of reversal of flux. That is, always it will produce a unidirectional torque. Now what will happen is, now let us look at the construction. Looking at the construction, it will be quite clear. Now here we can see that there is a fixed coil and a movable coil. Now if we see, the same current will flow through the fixed coil. That same current will only flow through the movable coil. That is, if plus 5 quantity plus 5 ampere is flowing, the current will be flowing in this direction. Here also the current will be the same. That is, if this is north, similar will be similar type of magnetic poles will be induced. If the direction of current is getting reversed, that is, if it is minus 5 ampere, the same here, if it is north, the magnetic fields will be changed. That is, depending on how the current is flowing, I can easily reverse the direction of flux, or the reversal of direction of flux is easily reversed, and because of this, always unidirectional torque will be produced. That is, for both positive and negative half of the cycles, the field can be made to reverse simultaneously. Why? Because the current in the movable coil and the fixed coil, as these both are connected in series, the current in both will be same. Now we can say that to reverse the direction of flux, each time the current through the movable coil reverses, and unidirectional torque will always be produced. So this is the basic principle based on which an electrodynamometer type instrument is working. Now talking about the construction, we have some major parts, that is fixed coil, moving coil, control system, moving system, damping, shielding, case and scale. So these are the basic major parts that we are having in a electrodynamometer type instrument. Now let us look at these. What are all these? Now let us look at the first thing. That is, first thing is fixed coil. Now fixed coil is, as we can clearly see, that the field, that is the field in which my moving coil is going to operate, is generated by the fixed coil. Now fixed coil, we can see that this is divided into two sections. That is, this is the first section and this is the second section. Now we can clearly see that it is surrounding the moving coil. Now as it is surrounding the moving coil, it gives more uniform field and it will help in the passage of the shaft. For example, if coil, if it is concentrated at one end, I will not get uniform movement. So to avoid that, what we are doing is we have split the moving fixed coil into two parts. Now this coil, it has air core. Air core means, that is, initially in the moving coil type of instrument, what we did is we used a former, and on the former for mechanical support, we used the former for mechanical support, and the coil was wounded on the former. Now here what we will do is, here there will be no cores, that is, no core will be using. We will be directly winding the, we will be just turning the wire and to get a coil. Now we can clearly understand that if I am going for air core type of coils, the coil will not have any mechanical strength. So to increase the mechanical strength, the coils are varnished and baked to form a solid assembly. Then they are clamped to coil supports. This makes the construction rigid so that there is no shifting or change in dimension which will affect the calibration. For example, if the size of the coil was this, when it is sitting for a longer period of time, it is possible that the coil will spread. Now as the coil is spreading, when the coil will spread, I'll again have to calibrate this. Or for example, this was the total height of the coil, when it winding was done. So because of gravity, what will happen is it is possible that this height or area may be changing. So this is a problem. So that we have to give rigid, that is we have to give rigidness to this coil. So this process, that is varnishing and baking process, we are undertaking to give rigidness to the coil. Now another thing that can be done is we can use some ceramic mounts we can use, or some ceramic parts we can use, replacing the the metallic part. Ceramic former I'll use, and on this ceramic former I'll wind my coils. Now when I'm doing this, what will happen is there is no weakening of the field in the fixed coil, and there is no eddy currents that are formed. The second part that we have is a moving coil. The moving coil is also either wound as a self-sustaining coil on a non-metallic former. The moving coil is also made in this similar manner. The moving coil is light. Why it is light? Because it is the moving part. So if it is having more weight, easy movements, I will not get easy movement of my pointer. So it is light in construction, but it is also rigid. We have to note one thing here, that both the fixed coil and the movable coil both are air core. Air core means what? There is no metallic former or no metallic parts used for the mechanical support or for mechanical support of the coils. Therefore these both are air cored type of instrument. And the third part we are having is control. Now the controlling torque, as we all know that here also we will be using spring control, hair springs we will be using. Then the moving system. The moving system is a aluminium spindle. I am using an aluminium spindle. To this aluminium spindle I have attached my spring. To this aluminium spindle itself pointer is attached, and there is counterweights also attached to balance the pointer, and to one end of the I am having bearings as well. I am having to the ends of the spindle. Here to this only the moving coil is also attached. So the moving system, it consists of aluminium spindle. It carries all the counterweights, the pointer, the suspension, all these things are attached to the moving system. The next thing that I am having is damping. Here also I will be using air friction damping. Why? Because eddy current damping cannot be used here as well, because if I am using eddy current damping, it will weaken the operating magnetic field. So because of that it will be less, therefore eddy current damping will not be preferred. We will be using air friction damping will be using. The next thing that I am using is shielding. Shielding has to be provided. Why shielding has to be provided? Shielding is provided because already the instrument, it has weaker magnetic field compared to permanent magnet moving PMMC type of instruments or MI type of instrument. These has weaker magnetic fields. So it is possible that any external interference or external magnetic fields can directly interfere with the operation of this instrument. So I have to give a shielding, that is I have to protect this from external magnetic fields. Now this is achieved by making a case of high permeable alloy. Then the next, the last portion is cases and scales. Now laboratory standard instruments, what we'll do is we'll hide this inside, or we'll prepare a wooden, highly polished wooden case we'll be preparing, or sometimes glass is coated with some conducting materials to completely remove electrostatic effects. To remove electrostatic effects and stray magnetic effects, we'll be using some casing and some scales we'll be using. Now as I have said, this electrodynamometer type instrument, this can also be used for DC. Now how this can be used for both AC and DC? From the construction itself, it is quite clear that always it will be providing a unidirectional torque. So as unidirectional torque is provided, whether I am using AC or DC, it will give the same pointer movement. Now let us look at the torque equation. Now looking at the torque equation, we can see that the mechanical energy, that is the work done, it is equal to Ti into d theta. Ti is nothing but the instantaneous torque, and when small amount of torque is applied, only a small amount of variation in position is possible. Therefore it is Ti into d theta. Now here we can see that the movement is because of the current in this fixed coil and the current flowing in the moving coil, and it is also dependent on the mutual induction in between both these coils, the mutual induction that is happening between these two coils. Therefore the torque, it is directly Ti d theta is because of I1, I2 and Dm, that is current flowing through the fixed coil, current flowing coil, and the mutual inductance, any small amount of mutual inductance that is happening in between these two. Because Ti I am taking it to be the instantaneous value, therefore I am taking Dm, the value of Dm, to be the rate of change of mutual inductance. Therefore I can write Ti, that it is equal to I1 I2 Dm by d theta. Now the control torque, it is because of spring, so I know that Tc, if I am using a spring, I will be writing it to be k theta. I am getting two equations, 1 and 2. Now if I am moving for DC operation, what will happen is, when I am talking about DC, the current, instantaneous current I1, I can replace it with capital I1, I2 I can replace it with I2, Dm, that is this small Dm, what I will do is, I will just keep it to be Dm by d theta. Now I can write Td is equal to I1 I2 Dm by d theta, that is rate of change of mutual inductance, that is dependent on the position, that will be dependent on position. So I can write at final steady state position, my Td is equal to Tc. Now when writing this, I get I1 I2 Dm by d theta is equal to theta. So I can write theta is directly proportional to I1 into I2. For example, the value of I1 is plus 5 and the value of I2 is plus 2. What I will get is 5 into 2, 10 I will get. Now when the direction of I1, that is if I1 is becoming minus 5, I2 will also become minus 5. So I will get, that case also I will be getting plus 10 I will be getting, that is for DC operation. Now for the AC operation, what will happen is, the current's value will be sinusoidal. Therefore I1 is equal to Im1 sin omega t and I2 is equal to Im2 sin omega t minus 5. Why? Because there will be small amount of mutual inductance, and because of as the moving coils, they are inductive in nature, because of that a small phase difference is possible. Now what I will do is, I will just add both these into this equation, that is if I want to achieve the total deflecting torque, what I will have to do is, I will have to integrate from a period 0 to t, that is for one full cycle I have to integrate, then only I will get what is the average deflecting torque. Now for getting the average deflecting torque, what I am doing is, I will just have to substitute the values of I1 and I2 here. Substituting the values of I1 and I2 and solving for that, I am getting Im1 into Im2 divided by 2 cos phi Dm by d theta. Dm by d theta, it is a constant quantity, therefore it cannot be differentiated, it cannot be integrated, because I am integrating with respect to dt. Now what I will do is, Im1 by root 2, it will give me the RMS value of I1, and Im2 by root 2, it will give me the RMS value of I2. Therefore I am replacing these maximum values with the RMS value. So I am getting Td is equal to I1 I2 cos phi Dm by d theta. In the final position, we know that deflecting torque is equal to controlling torque, therefore I am taking it to be Td is equal to Tc, and solving for this, I get the value of theta is equal to I1 I2 by k cos phi Dm by d theta. Here also we know that theta is directly proportional to I1 by I2, that is for both the case of DC and for the case of AC, we can see that theta is equal to theta is directly proportional to I1 and I2. So as in the previous expression as well, here we can see that unidirectional torque will be produced for an electrodynamometer type instrument, and this electrodynamometer type instrument, it can be used for both AC and DC. So in today's lecture we have discussed about PMMC instruments. PMMC instrument, theta was directly proportional to I. Then we discussed about MI type of instruments. Here theta was directly proportional to I squared. Therefore this MI type of instruments can be used for both AC and DC. PMMCs can only be used for DC type of instrument. The third type of instruments that we have discussed is electrodynamometer type instrument. So in electrodynamometer type instrument, we have seen theta is directly proportional to I1 into I2, and this electrodynamometer type instrument can be used for both AC and DC. So these are the three different type of instruments discussed in today's lecture.